Good morning, everyone, and thank you for joining us today for this webinar with Task Force and Rohde Schwarz from the Test Essentials series, Signal Generator Basics. Without further ado, let's get started.
Hello, and welcome to this presentation, Test Essentials Signal Generator Basics. In this presentation, we'll cover the two main types of signal generators, beginning with analog signal generators. In the case of analog signal generators, we'll discuss the importance of signal quality, as well as the most common analog modulation types. The second main type of signal generator is vector signal generators. In this section, we'll start by explaining what we mean by vector signals, as well as the modulation types and applications most commonly found when using vector signal generation. The concepts of baseband and IQ will also be introduced, followed by an overview of the different impairments and fading that can be created using a vector signal generator. And we'll end the presentation with a general summary of what we've covered. Before we go into more detail, let's start by talking in a broad way about the difference between analog and vector signal generators. Signal generators can be divided into two major categories: analog signal generators and vector signal generators. Analog signal generators are primarily used to create so-called CW, or continuous wave signals, in other words, unmodulated carriers. Analog signal generators can also be used to generate signals with analog modulation, such as amplitude modulation, frequency modulation, or phase modulation. In addition, many analog signal generators can also generate basic unmodulated RF pulses. And there are also a few special types of purely analog modulation, such as the various Avionics standards, that can be generated using an analog signal generator. A vector signal generator, on the other hand, can create any arbitrary type of digital or analog signal. For example, a vector signal generator can produce different types of digital modulation, such as the different flavors of Wi-Fi, cellular standards like LTE and 5GNR, GPS and other global navigation systems, etc. They can also produce special non-digital waveforms like multi-carrier CW, where a large number of individual tones are produced. Vector signal generators can also play out so-called arbitrary waveform, or ARB files. And unlike analog signal generators, many vector signal generators can introduce various signal impairments like noise and interferes, as well as fade the generated signals to model real-world propagation effects. Given all the flexibility of vector signal generators, why would anyone ever use an analog signal generator? There are actually many applications whose requirements can, or should, be met using analog signal generators. Analog signal generators are used whenever high-quality signals are needed, for example as a local oscillator substitute. They can also be used when making basic but essential RF parameter tests like gain, linearity, bandwidth, etc., and are therefore often a good choice for component tests, such as the development of analog to digital converters. In many cases, such as in receiver testing, we only need basic signals to verify functionality. EMC, or electromagnetic compatibility testing, uses analog signal generators almost exclusively. And as mentioned a moment ago, for certain special applications like avionics or military radar applications, analog signal generators are a good, if not the best, solution. Analog signal generators have two advantages over vector signal generators. They usually cost less, but more importantly, they provide very high-quality signals. Let's talk about this second point in a bit more detail. If there's one thing that analog signal generators excel at, it's creating high-quality RF signals. Signal quality can be divided into three performance areas. The first has to do with frequency and includes things like accuracy and stability. The next area is level performance. Linearity and repeatability are important concerns here. And last but certainly not least, we have spectral purity. Both phase and wideband noise, as well as the suppression of harmonics and spurious signals, are key components in spectral purity. It bears repeating that if we want high-quality RF signals, analog signal generators are often the best choice. The most fundamental signals produced by a signal generator are simple unmodulated signals, which have only two configurable parameters, frequency and level. Remember that high-quality, spectrally pure CW signals are a very important part of many application and test scenarios, such as local oscillator substitution, or the testing of analog to digital converters. And for those cases where we want to change the frequency and/or the level of CW signals, list and sweep modes can be used to change or switch between user-defined limits, states, or values. In addition to CW signals, an analog signal generator can also generate signals with analog modulation. As you probably already know, the three basic types of analog modulation are amplitude modulation, frequency modulation, and phase modulation. Despite the tremendous growth in digitally modulated signals, analog modulation is still very important for many applications, and it's used in a wide variety of design, test, and debug scenarios. A special type of analog signal modulation is pulsed signal generation. Most analog signal generators can also create basic unmodulated pulses. The unmodulated RF carrier is essentially switched on and off to create the pulses. Unmodulated here means that the RF carrier doesn't change in frequency, amplitude, or phase during the pulse. Pulses can be sent at fixed intervals, but in some cases the analog signal generator can vary the pulse width and/or pulse spacing by means of a user-defined list. If we need more complex or modulated pulses, such as a chirped or a polyphase pulse, we usually need to use a vector signal generator. In addition to generic AM, FM, PM, and pulse modulation, there are some other applications for analog signal generators. For example, analog signal generators can be used to create many of the signals used in avionics, that is, signals used by aircraft for navigation and landing. These include things like VHF omnidirectional range, or VOR, both localizer and glide slope signals in ILS, or the Instrument Landing System, as well as signals from marker and non-directional beacons. Since the main strength of analog signal generators is their ability to deliver high-quality signals, the primary criteria when selecting analog signal generators are largely related to signal purity. Phase noise, or the short-term stability in the frequency of the signal, is extremely important in many applications, since the effects of excessive phase noise can create many types of problems. Similarly, the level of harmonics or other spurious products should be as low as possible. Another important criterion is output power, or more specifically, support for higher output powers. Having a higher max output power helps to preserve spectral purity by avoiding the need for additional external amplification. Secondary criteria include things like switching speed, or how quickly the generator can change the frequency and amplitude, as well as amplitude accuracy of the generated signal. And finally, support for purely analog modulation types, such as the avionics standards we just mentioned, can also be important when choosing an analog signal generator. Now that we've covered analog signal generators, it's time to move on to vector signal generators. But before we get started, we need to explain what the difference is between analog and vector signals. An analog signal is defined by a magnitude alone. In other words, it's a scalar value. A vector signal is defined in terms of both a magnitude and a phase. Vector signals are the method of choice for sending digital information, or bits. Let's look at how this might work. For example, we could define 4 different states or symbols, each with the same magnitude, but with different phases. Each one of these symbols, or distinct magnitude phase pairs, would then correspond to a unique 2-bit pattern. We indicate which pair of bits we're sending by choosing which of these 4 combinations of magnitude and phase we transmit. This type of vector modulation is used in almost all digital modulation schemes. This includes things like LTE, 5GNR, Wi-Fi, Bluetooth, etc., etc. In most cases, however, a much greater number of possible states or symbols is used to send more bits for each symbol. But how do we tell a vector signal generator which amplitude and phase values to use when generating RF signals? Instead of representing a vector as a magnitude and a phase, we can use basic trigonometry to represent this vector as 2 magnitudes, a real or in-phase magnitude and an imaginary or quadrature magnitude. Quadrature just means offset by 90 degrees. In the RF world, vector signals are usually represented as so-called IQ values, consisting of a real and an imaginary value. Using IQ values greatly simplifies vector signal generation and analysis. A vector signal generator, therefore, produces modulated signals using these IQ values, which contain both a magnitude and a phase. These IQ values can be provided to the generator in a number of ways. In most cases, the source of the IQ values is internal to the signal generator. One way of generating IQ values is producing them in real time within the generator itself. Examples of this would be some type of custom digital modulation that uses a repeating or a pseudo-random bit sequence as its source, or the simulation of GPS and other global navigation systems. For most types of digital modulation, such as LTE, Wi-Fi, etc., the IQ values are pre-generated internally for some defined period of time, usually in units of frames or subframes. Another common way of generating vector signals is to load a pre-existing file containing I and Q values. These arbitrary waveform or ARB files are usually created using either a special software application or tools such as MATLAB. Alternatively, IQ can be provided by an external analog or digital source. Note that in both cases, that is, arbitrary waveform files or external I and Q, there's no industry-wide standard for IQ data representation, although tools usually exist for converting different file formats. One last important note. You'll often hear the term baseband used to refer to IQ signals before they're converted to RF. So what are the most important applications for vector signal generators? Clearly, vector signal generators are needed whenever we're generating vector signals, such as those found in wireless communications, digital broadcast, GPS, and other global navigation systems. Vector signals can also be used to generate multiple signals to simulate multi-antenna systems, such as those used in MIMO, or multiple in, multiple out, and beamforming applications. And as we'll discuss later in this presentation, one of the advantages of vector signal generators is their ability to simulate signal impairments, such as noise, interference, fading, etc. This is particularly important when testing receivers under real-world conditions. It might be helpful to walk through a block diagram of a basic vector signal generator. As we just discussed, the baseband is where the IQ data is loaded or generated and filtered if needed. The IQ modulator is used to upconvert these baseband signals to RF. The RF block is where we set things such as frequency, level, etc. Note that in most cases we can also use our vector signal generator as an analog signal generator by configuring analog modulation such as AM, FM, etc. in the RF block. We'll look at each of these blocks in more detail in just a moment. But before we talk about the sources of baseband or IQ data, we need to spend a moment discussing something called the bandwidth of a generator. Simply put, the bandwidth of a vector signal generator represents the widest signal that can be faithfully created, and the amount of available bandwidth is a function of the generator design. For example, if we wanted to create a 10 MHz wide LTE signal, we would need a generator with a bandwidth of at least 10 MHz. Traditionally, most vector signal generators had bandwidths in the tens or low hundreds of megahertz, but many modern communication technologies, such as 5G or the newer flavors of Wi-Fi, require bandwidths in the high hundreds of megahertz or even low gigahertz. One of the more important considerations when choosing a vector signal generator is to be sure that it has sufficient bandwidth for the intended application and for future applications as well. A special challenge when using wider bandwidths in vector signal generation is the need to preserve spectral flatness across these very wide ranges, or when changing frequency. As signals get wider, the flatness of the signal becomes more and more important. We want to ensure that our generator isn't introducing amplitude errors at any point over a very wide frequency range. For example, making sure that our amplitude error is less than 1 dB over a bandwidth of 2 GHz. This might seem like a somewhat demanding requirement, but remember that many modern modulation schemes require good RF performance over very wide bandwidths. One way of achieving flatness is to run some type of separate external calibration routine, but this is extremely time-consuming and would have to be repeated every time the signal frequency changes. The more modern approach is to integrate an internal level sensor and adjustment routine into the generator itself. This is significantly faster and has the advantage of preserving spectral flatness even while the generator frequency is being changed. The next question is, how are baseband signals created? Remember that we use the term baseband to describe IQ data before it's converted to RF using an IQ modulator. We can obtain this baseband data in real time from an external source, either in analog or digital format, although some conversion or conditioning may be required. We can also create an arbitrary waveform or ARB file externally and then loaded into the vector signal generator's ARB memory, usually either via a LAN connection or USB. ARB files can also be created within the generator itself using a graphical user interface to specify modulation parameters. And in some cases, IQ data signals can be created internally using a real-time generator, which can produce IQ values for any given duration of time. Note that a single baseband can only process one source of IQ data at a time. That said, many vector signal generators support multiple basebands, whose signals can be created either independently or combined. Let's look at each of these sources of baseband information a bit more closely. Internal or external generation of ARB files is, by far, the most common way that vector signal generators are used, but IQ data can also be provided to vector signal generators over external analog and/or digital IQ inputs. This external input is used, for example, when the signal is created in an external baseband arbitrary waveform generator. Another common example of where external IQ input is used is the case in which RF signals have been captured and/or stored as IQ data, and these values are then streamed to the vector signal generator in order to recreate or play back the captured signal. Most often, B and C connectors are used for analog IQ data, and proprietary connectors are used for digital IQ data. And although most vector signal generators are intended to produce RF signals, many can also output their basebands as IQ data using these same connectors. The other way of using IQ data created external to the vector signal generator is in the form of arbitrary waveform, or ARB files. Here the waveform is pre-calculated. The IQ values are not generated in real time. These pre-calculated values are stored in a file containing pairs of IQ values. Arbitrary waveform files can be created in two main ways. The first is using tools such as MATLAB to generate the I and Q values. This is usually a very time and labor-intensive process and requires expert knowledge of things such as signal processing and the specific modulation type. A more common method for creating ARB files is using a special software application, often provided by the instrument manufacturer, with a GUI-based interface for specifying the parameters of a given modulation type. As the name arbitrary implies, an ARB file provides complete flexibility in the characteristics of the signal. Any arbitrary signal can, theoretically, be created by generating the appropriate I and Q values. The main limitation when using arbitrary waveform files is size. The length of the waveform is limited by the maximum number of samples that can be stored in the vector signal generator's memory. Arbitrary waveform files can also be internally generated, that is, inside of the vector signal generator without using any external software or a computer. In this case, a graphical user interface is used to specify the desired modulation type and configure the modulation parameters. This created arbitrary waveform file can be stored in the generator's internal memory and/or saved as a file. This is significantly easier than generating an ARB file externally. Let's look at an example of how this is done on a typical vector signal generator. For our example, let's say that we wanted to create an LTE downlink signal. On our generator, we would simply select LTE from the list of available baseband modulation types, and then use a simple graphical user interface to specify the general parameters, uplink or downlink, FDD or TDD, etc. Additional dialogues allow us to configure the characteristics of our signal, as well as to define the contents of our transmitted frame and subframes in whatever level of detail is required. Being able to perform this kind of signal configuration directly on the generator, as opposed to using external tools, greatly increases the ease and efficiency of defining vector modulated signals. The end result of this process is an arbitrary waveform that can be immediately generated by our instrument and/or saved for future use. As we've just seen, we can create arbitrary waveform files either externally, using a special software package or tools like MATLAB, or we can create them internally to the instrument, usually using a graphical user interface to specify the modulation parameters. But the question now is, how do we play out these files? It's important to remember that when we create waveforms for most modulated signal types, we usually do this on a frame or a subframe basis. For example, communication standards like LTE, 5GNR, etc. all have a frame structure, and when waveforms are created for these signals, the minimum unit is one of these frames. Note, however, there are some types of signals that may not have this defined structure. We can have our vector signal generator play out waveforms in different ways. For example, our generator might produce the waveform only a single time, repeat the waveform over and over, or play out the waveform when some type of external trigger signal is received by the generator. We just saw how an incoming external trigger can be used to tell a vector signal generator when to play out a waveform. On the other hand, some test scenarios require synchronization with a generated waveform, that is, a knowledge of when the waveform or part of a waveform is being transmitted. This is done by means of markers. Markers are a kind of outgoing trigger signal that indicates when a waveform, or a certain part of a waveform, is being generated. For example, we could use a marker to indicate the start of each transmitted frame. The use of markers requires some type of secondary connection, usually a BNC cable, between the generator and receiver. Predefined arbitrary waveform files can be used to generate very complex modulation schemes and standards, but they have fixed values and relatively short durations. Vector signal generators can also generate signals in real time based on various user-configured parameters. In this case, we start by defining the modulation type, such as FSK, PSK, QAM, etc. Next, the various modulation parameters, such as symbol rate and filter, would also be defined. And finally, we define which data is being transmitted. This can be in the form of a file, a repeating pattern, such as alternating ones and zeros, or a so-called pseudo-random bit sequence, or PRBS. PRBS data looks random, but is actually a known repeating pattern. Since the generator is creating the symbols in real time based on these defined parameters, very long sequences can be generated. There is no length limitation, such as there is with static, predefined ARB files. And likewise, the generator memory requirements are also quite low, since we're not pre-generating and then storing pairs of IQ values. One example of where real-time signal generation is helpful is in bit error rate testing, where we want to send a known pattern of bits and determine which percentage of these bits are correctly or incorrectly decoded by the receiver. Another example of real-time signal generation involves simulating GNSS, or Global Navigation Satellite Systems. The best-known examples of GNSS are the American GPS, or Russian GLONASS systems, which provide location and timing information worldwide. In order to test a GNSS receiver, a vector signal generator must simulate the signals from multiple satellites over longer periods of time. Receivers require time, often on the order of minutes, to lock onto the signal, and receiver testing may require the receiver track satellites for very long periods of time, up to hours or days. Furthermore, the GNSS satellites are not fixed in the sky, but rise and set, so the signals from each satellite will be changing dynamically. It should be clear that a static ARB file with a duration of only a few seconds couldn't be used to test a GNSS receiver beyond basic RF parameters such as receiver sensitivity. A vector signal generator can, however, generate realistic signals and emulate a GNSS constellation over longer periods of time by using user-supplied data regarding the satellite constellation, such as current time and date, receiver location, etc. Now that we've discussed the different ways that IQ values can be generated, let's take a moment to discuss how these values are converted into RF. Vector signal generators convert INQ values into RF using something called an IQ modulator. When using IQ values for modulation, these are split into two paths, one for I and one for Q. These signals are mixed with an oscillator, and in the Q path, the oscillator signal is shifted by 90 degrees. This ensures that the I and Q signals do not interfere with each other when they are combined and transmitted. Although it's helpful to understand the basic principles of an IQ modulator, in normal operation, the user of a vector signal generator doesn't need to adjust the IQ modulator or its settings. The last block in our vector signal generator is the RF block. This is where we specify the characteristics of the generated RF signal, such as frequency and level. We can also use this block to apply various types of analog modulation, such as AM, FM, PM, etc. Remember that a vector signal generator is also capable of generating signals with purely analog modulation as well. And finally, this block can step or sweep through user-defined values of frequency and or level, which is important in many types of testing. The three building blocks of our vector signal generator were the baseband, the IQ modulator, and RF. However, many vector signal generators can also allow the addition of signal impairments in the forms of fading, different types of noise and interferes, and IQ impairments. These different types of impairments emulate the kinds of real-world effects seen in RF systems and applications, and therefore the ability to add definable and controllable impairments is important in the design, test, and debug of radio frequency devices. We'll start by looking at noise and interferes. There are four main types of baseband impairments that can be created by vector signal generators. These include noise, or more precisely, additive white Gaussian noise, or AWGN, CW, or continuous wave interferes, impulse noise, and phase noise. Let's start by discussing noise, or AWGN. AWGN stands for additive white Gaussian noise. Additive means the noise is combined with a useful signal, as shown here. Adding the noise in the baseband is much easier and much more flexible than doing this at RF or externally. White refers to the power of the noise as a function of frequency. White noise has, ideally, the same power at every frequency. And Gaussian describes how this noise changes over time. It increases and decreases over time with a Gaussian or bell curve shaped distribution. Being able to add AWGN to our signal is extremely useful because this allows testing under real-world conditions where noise is an unavoidable fact of life, so to speak. By using a vector signal generator to generate this noise, we can create a signal with a definable, controllable signal-to-noise ratio, or SNR. As mentioned a moment ago, this is advantageous when testing things like receiver sensitivity, or when performing bit or block error rate testing. Although this block in our vector signal generator is labeled AWGN for additive white Gaussian noise, it's also possible to generate a noise-only signal with a definable width and power. Being able to generate a pure noise signal is useful in some types of testing, even when no modulated signal is present. Another common type of interfere that can be created by vector signal generators are so-called CW, or continuous wave interferes. These are essentially unmodulated carriers with a very narrow spectral width. CW interferes are commonly used in receiver blocking tests, which test the ability of a receiver to correctly detect and or demodulate a signal in the presence of a second interfering signal. A vector signal generator can place a CW interfere near the useful signal or within the useful signal itself. In addition, the power level of the interfere can be adjusted relative to the level of the useful signal. Although it's not difficult to use a second signal source to create a CW signal and then mix the two signals together, doing this as a baseband impairment provides much more control over the signal position and power. And more importantly, it also eliminates the need for an entire second RF path or generator for creating a simple interfering signal. Although the level of AWGN, or additive white Gaussian noise, does vary over time as per a normal or a Gaussian distribution, these changes are relatively small, and the noise never goes to zero. Impulse noise, on the other hand, has an on-off or bursty pattern. There are actually many types of real-world sources of impulse or bursty noise. Some of these are unintentional sources of RF, such as spark plugs, etc., but there are also numerous intentional sources of pulsed energy, with radar being an obvious example, as well as some digital modulation schemes that transmit energy in short bursts. Some vector signal generators can create impulse noise and add it to the baseband signal by defining the width of the pulse noise, the number of pulses, and the interval between the pulses. The ability to add these impairments to the baseband signal makes it possible to test under more realistic conditions with a minimum of additional equipment and effort. The next type of impairment we'll discuss is something called phase noise. Phase noise is short-term variations in the frequency of a signal. A signal with a fixed, non-changing frequency looks like a thin line in the frequency domain and a stable sine wave in the time domain. If the frequency of the signal changes, we see a spreading of the signal, or skirts in the frequency domain, and a jittered signal in the time domain. Some amount of phase noise is unavoidable, but excessive amounts of phase noise can cause many different kinds of problems. For example, phase noise can cause high levels of error vector magnitude, or EVM, in communication systems. In radar systems, phase noise can lead to errors such as the masking of slow-moving targets. Normally, we want a signal generator with the lowest possible phase noise, but in some cases, it's helpful to be able to add a controllable, user-defined amount of phase noise to a generated signal for device testing. A vector signal generator adds phase noise to the baseband signal by defining the amount of phase noise at given frequency offsets from the nominal carrier frequency. For example, we tell our generator to add minus 70 dB of phase noise at an offset of 100 Hz from the carrier, minus 93 dB at a 10 kHz offset, etc. Increasing levels of phase noise can be seen, for example, in constellation diagrams, where the signal points rotate, leading to increased bit errors. Adding controllable and definable amounts of phase noise to the generated signal can therefore be used to determine the maximum acceptable level of phase noise in components, systems, etc. Now that we've covered noise and interferers, let's move on to the more complicated case of fading. Fading models the effect of real-world signal propagation. There may, for example, be a direct line of sight between transmitter and receiver, or the signal may reflect or be diffracted by larger objects. Smaller objects with irregular surfaces can cause scattering of a signal. An intervening object may attenuate or block signals entirely for shorter or longer periods of time. Furthermore, relative movement of the transmitter or the receiver will result in Doppler shift, or a change in the frequency of the received signal. As we've just seen, in the real world, multiple copies of the signal can arrive with different delays, different levels, and different frequencies. We can model these echoes with similar delays as so-called taps. Each tap has a defined delay, attenuation, and fading behavior. Fading behavior includes things such as the time-varying pattern of the fade. For example, Ricean fading generally is constant over time, whereas Rayleigh fading occasionally will exhibit deep fades. Once we've provided this information, a vector signal generator can then fade the signal appropriately for each tap. Note that many wireless communication standards, such as LTE, require that devices be tested with standardized fading profiles that simulate a wide variety of real-world environments, such as being in a large city or on a fast-moving train. Noise, interferers, and fading are baseband impairments. The last type of impairment we'll discuss occurs in the transition between baseband and RF, that is, in the IQ modulator or demodulator. When we represent signals as IQ values, these signals should be, exactly, 90 degrees apart and should also have identical amplitudes. Any imperfections in the IQ modulator or demodulator can lead to errors in converting the baseband signal to RF or vice versa. Note that these errors are a function of the transmitter or receiver, not a function of propagation. Being able to introduce controllable IQ impairments can be very helpful in receiver testing, and vector signal generators can also introduce various IQ impairments, such as quadrature offset, where the angle between the components is not precisely 90 degrees, or gain offset, where I and Q have unequal amplitudes. It should be clear that a vector signal generator represents a significant step up from analog signal generators in terms of the type of signals it can produce. When selecting a vector signal generator, one of the most important criteria is bandwidth, since this defines the widest signal that our generator can produce. Remember that the bandwidth required for modulated signals such as LTE, 5GNR, and the more modern versions of Wi-Fi or 802.11 can require bandwidths in the hundreds of megahertz, so it's a good idea to select a vector signal generator that can meet requirements both today and in the future. Closely related to bandwidth is spectral flatness. As mentioned before, one of the challenges in creating very wide vector signals is ensuring a constant level control over the entire bandwidth, and this flatness is therefore an important consideration for wideband signals. Regardless of bandwidth, we also want to be sure that our vector signal generator is creating as clean of a signal as possible, which means minimizing the level of phase noise, as well as amplitude and other errors that can lead to higher levels of EVM, or error vector magnitude. Among the most common secondary criteria are things such as output power. Just as with analog signal generators, we want to avoid situations that might require an external amplifier, since external amplifiers can degrade the quality of the generated signal. The maximum arb memory is also important, as this defines the maximum signal duration of our arbitrary waveform file. And finally, there are numerous other special features or application-specific options that are available on different vector signal generators. In this presentation, we've touched on some of these, such as the ability to add various types of baseband impairments, but there are many other special applications that can be addressed using the flexibility provided by vector signal generators. So let's summarize the main points regarding analog and vector signal generators. Analog signal generators are most often used when creating basic CW signals, where signal quality is most important, although they're also used for many types of analog modulated signals. Vector signal generators, on the other hand, are most often used when generating signals with digital modulation, particularly when these signals are vector signals that have both a magnitude and a phase. The signal chain in a vector signal generator involves creating a baseband signal, converting this to I and Q, and then converting the IQ values into a radio frequency signal. One further application of vector signal generators is the addition of impairments and fading to simulate real-world propagation effects. And with that, we've reached the end of our presentation on signal generator basics.
Okay, we're now going to open up the floor to any questions. So if you have a question, please type it in the Q&A box, or if you'd like to raise your hand, we can unmute you. So I guess we can start with, we got one during the presentation. Paul, did you want to start with that question?
Sure. There was a question that we saw that I have a requirement for a 28-volt peak-to-peak sinusoidal function. SigGen and function generator have a max of 20-volt peak-to-peak. Does RNS have a solution? Typically, of course, what we've been discussing mostly in this presentation has been RF signal generators. The difference is, of course, for signal generators that are operating at RF versus what most people would call a function generator, where the functions are being produced at much lower frequencies, say maybe up to tens of megahertz, no more. In both cases, the output power is really a function of the generator. For an RF generator, of course, you would have to know the impedance that it's being operated into. Rohde Schwarz does have generators that go up to plus 30 or plus 38 dBm. So I'd have to do the math there to figure out what that is into a given 50 ohm load. In terms of a regular function generator, so not an RF, but what I'll call an electrical function generator, Rohde Schwarz makes those as well. I would have to check about the maximum output power. Typically, though, usually an amplifier would be the simple solution to get around this, especially if you're talking about an electrical function generator, and I believe that's what the question is here. Getting some kind of fairly linear amplifier at that range would, oh, thank you, someone's doing the math for me. Plus 33 is 28 volts peak to peak. Wonderful. We do have a generator that an analog signal generator that goes up to plus 38. So that should be fine to put you over that limit. So I guess the question's sort of been answered by the questioner. But in cases where you don't, you can put a simple amplifier in front of it. One of the reasons why we do have a high power output for some of our signal generators is simply because in many cases the amplifier, well, one, it's an additional piece and it could cost a certain amount of money. And also there are concerns about the linearity of it. I mean, anytime you add an additional amplifier, an additional active device to a signal chain, you run the risk that that active device will create problems. It'll introduce noise, for example. If you push it into compression, you can have all kinds of undesired products. So it's often easier to have a generator that goes up to that high power level. And again, this is one of the reasons we have a high power option for one of our analog signal generators that takes up to plus 38 dBm.
Okay, great. I have another question here that I don't think you can see, Paul. It looks like it was just sent to me directly.
Sure.
So this person is asking, which is the best signal generator to produce both a carrier wave or an externally triggered modulated signal that can be delayed and capable of producing single, double, and triple pulses at the range of 1 to 3 gigahertz at the signal level of plus 20 dB to negative 110 dB.
Sure. Well, I'm assuming that if you're doing external pulse if you're doing what I'll call unmodulated pulses, that is simple on and off pulses, not pulses that have some kind of chirp or phase changes in them. In that case, the best application would really be an analog signal generator. I know for Rohde Schwarz, all of our analog signal generators have an external pulse input, and there are various ways to control how the pulses are produced. We also have the ability, in terms of pulse input, to generate single, double, and arbitrary trains of pulses. Typically, when you're doing pulse signal generation, I actually do have a video that just went up about a week ago on YouTube, on the Rohde Schwarz YouTube channel about this. You can actually have the generator be triggered from an external source and then produce these double, single, or triple pulses, basically in any pattern that you want to. The power levels that you mentioned are typical for a signal generator. Pretty much any signal generator, RF signal generator, should be able to produce pulses in that range. So in this case, you could use a vector signal generator for that. That does give you some more flexibility, but frankly, it's more expensive. Most signal generators, again, support an external pulse input. But in this case, I would probably recommend an analog signal generator. It tends to have somewhat higher quality in terms of the signals, the spectral purity of the signals, and it's considerably cheaper and simpler to run for this kind of application. I do see a question come up about LabVIEW drivers. Yes, all of our instruments support LabVIEW drivers. Test automation is very important for many people. So the ability to support LabVIEW, or I'll call it native programming. So if you use Python, if you use MATLAB, those are my two favorites personally. If you use Microsoft Visual C++, something like that, all of our instruments support remote control methods. We understand that a lot of customers actually they like to have a nice user interface, but after a while, a lot of customers often move to test automation, either for repeatability or speed or other functions. And so we do have complete support for remote control access, including LabVIEW drivers.
Great. Another question here. How do I capture an RF signal and replay it from a generator?
So in this case, you would need a vector signal generator, and obviously you need the captured RF signal. The way that this is normally done is that you have a spectrum analyzer, I should probably call it a signal analyzer, that has the ability to look at spectrum clearly, and then digitize it in the form of so-called IQ data, which is one of the things we discussed in this presentation. So I have a spectrum analyzer. It looks at a certain bandwidth. This depends on the generator. It could be tens of kilohertz up to tens of megahertz, sometimes more, and converts it into IQ samples at a given sampling rate. Once you have that data in IQ format, and this is just essentially a file with just columns of I and Q values, you can completely reconstruct the RF signal using a vector signal generator. You simply provide these IQ values to the vector signal generator and say, make this waveform, produce this file, and it will produce an exact copy, and I do mean exact, of the spectrum as seen, again, assuming you sampled it at a high enough rate. So that's not really a difficult thing to do. The hardest part really is getting the IQ samples that you want to play back. Playing them out of a vector signal generator is actually pretty easy, and something that's supported on all of our vector signal generators.
I have another question here. This person's asking how they can generate coherent signals with two separate generators.
Okay, well, I should probably, just in case, explain what I assume is meant here by coherent. Coherent is where the phase of two signals is related. So normally if someone says something is phase coherent, it means that the two generators in this case would have the same phase. So when I turn them both on, the sine waves they produce both start at, say, 0 degrees, and they stay locked. So at the point where one of the sinusoids is at 180 degrees, the one on the other generator is at 180 degrees. And in there are cases where you want them to be phase coherent and have the phases locked. So I want two signals that have exactly the same phase. The other time is sometimes I want them not to be locked, or rather not to be the same, but still locked. So I have one generator that produces a sine wave starting at 0 degrees, and another one producing a sine wave that starts at 90 degrees, and it maintains this 90 degrees phase relationship for both signals from each generator. This is actually, again, relatively easy to do with signal generators, either with analog or with vector signal generators. The only requirement really is that the signal generators share the same frequency reference or clock. Now, all of our signal generators, at least, have an internal clock that they obviously use. They can also be tied to an external reference. This is usually a 10 megahertz signal. It's fairly standard in the industry. So if you needed phase coherent signals with two generators, the simple solution is to have one of the generators produce the ref out signal of the 10 megahertz reference signal, and have the other one use that as a ref in signal. And that's usually done through a simple BNC cable connecting the two.
Looks like we have one more here. Can I create vector signals directly on the generator, or do I need to use an external software to do that?
It's a good question. For all of our instruments, you can do it either way. I should probably back up a step though and explain what it means. So typically, a signal generator will have a user interface, a graphical user interface. And in many signal generators, you can simply use that as this GUI to create the signal. So if I want to do just simple analog signal, I could say I want an analog signal with AM modulation at this frequency and this modulation depth and this power, and just using the interface, create that and send it out. And for vector signal generators, it gets somewhat more complicated because vector signals have, again, as we mentioned in the webinar, a lot of other parameters. And on our instruments, we support creating those directly on the instrument. Now, that said, there are, of course, customers, people who want to create the signals on a separate piece of software that is not sit in front of the instrument and do it, but do it at a proper desktop and a keyboard. We have support for that as well. The third one is something, again, I touched on briefly in the presentation. There are people who want to create their own waveforms essentially from scratch. A lot of times people do this in MATLAB. If you're designing, for example, a new product or a new device, you may need a waveform that we don't natively support, or maybe you have your own special, I'll call it flavor of that waveform. And this is something that many people, I think MATLAB is pretty much the tool of choice for this. The people will create a waveform in MATLAB and then can copy it to the generator and have the generator play it out. So those are the three. We support all three of them. Some generators, I mean, I know that we make very small, compact generators that don't actually have a GUI. It has to be done through a remote piece of software. But generally speaking, all of our instruments that are big enough to have a screen that you could touch with your finger support the ability to generate the waveforms directly on the instrument. It's only in the case of very small instruments that don't have the real estate for a screen that you might need to use external software. But again, the option is there for people who do want to create the waveforms in software using a separate PC or separate workstation.
Okay, great. I'm not seeing any further questions, so I'd just like to say thank you to everyone again for signing on for today's webinar, and thank you to our presenter, Paul. And if you think of a question later on, there's the email I was just talking about, or you can reply to myself. And if you're looking for any other great technical resources, like other webinars, white papers, or app notes, you can go to our website, testforce.com/academy. And we'll have another webinar coming up soon from the Rohde Schwarz Everything Test Series, and that will be on April 20th with the topic of Spectrum Analyzer Basics. Have a great day, everyone, and thank you again.
Thanks, everyone.